Hello and good afternoon, and welcome to the new episode, which is directed to the A-level candidates. In this episode, I'm going to solve three different questions about analysis. These questions are related to the organic chemistry, and we in the last chapter, we have techniques. By using these techniques, you are going to identify the organic compound, which functional group we have, how many carbons, how many hydrogens. So by using different techniques, for example, infrared, proton NMR, carbon 13 NMR, and also mass spectroscopy. So let's start with the first question. So this is a question about mass spectroscopy. So this question is about compound T. Compound, it's CXHYOZ. We don't know exactly what's the number of carbon or hydrogen or oxygen. But from A, part of the mass spectrum of T is shown. Here is very clear, the molecular mass of your compound, it's 150. Okay, and here we have two info. M, which is the peak heights of the M, which is 33.9, and M plus 1, which is 3.4. So by using these two info, we can calculate the number of carbons. How? By using this equation. So number of carbon equal what? Always you are going to M plus 1 over M times 1.1. Okay, this one, it's a fixed constant equation, and time 100. Let's apply this one. Number, you have M, which is 3.4, 3.4, yes, time 100 over 33.9 time 1.1. This one, it will give us 9. So number of carbon, it's 9. Okay, number of carbon, so here we have C9. Okay, H, oh, exactly, I don't know, but now the molecular mass is 150. So the mass of 9 carbons, the mass of 9 carbon, 9 times 12, it's 108. That means the remain is 42. This 42 could be 2 oxygen, which is 32, and 10 hydrogen. So here, if we are going to add 2 oxygen, so that means here you will subtract 32 from 42, you will have 10, and this one is 10. Okay, so Your compound is C9H10O2. Deduce the molecular formula C9H10O2. From this molecular formula, what's your compound? Here, let me explain this thing for you. Always, you have this compound C9, okay? The number of hydrogen, if it's saturated alkane, this one it will be C1820. But actually, how many hydrogen you have? 10. That means here you have subtract 10 hydrogen from 10. What does that mean? That means these 10 could be 5 double bond, or could be benzene ring plus double bond. Why benzene plus double bond? Because in the benzene, always benzene, if you have one ring, that means you need to subtract 2 hydrogen, and in the benzene ring you have 3 double bond, that means you have subtract 6 electrons, so total it's -8, and minus 2 double bonds. So your compound could be it's a benzene ring, and there is a double bond is bonded to the benzene ring. Okay, now he's asking about this one. The mass spectrum has peak at 119. It's very clear, this one at 119, and your compound 150. So what's the fragments? The fragments, to know the fragments, who is it? So you will say 150 minus 119, and this one it will give you 31. 31 could be CH3O. Okay, CH3O. Why? Because carbon 12 plus 3, you have 15 carbons plus 16, and this one it will give you 31. So your compound contain this group. Okay, so till right now we can say your compound it's benzene ring and this one, but how it's bonded we don't know, because still we haven't explained all the compounds, because here we have 6 carbons, 7 carbons. Till right now we have 2 carbons, because the formula it's C9. By using infrared, in the infrared you are going to determine the functional group. Only the functional groups. So he's asking about these 2 peaks at V and W. This one V, which is approximately at, okay, this one for carbonyl, and this one W, that means for this bond, carbon and oxygen, it's the single bond one. Okay, the single bond, not this one. So till right now we can summarize these things. Maybe our compound it's benzene ring, and there is carbonyl, and as we have said in the previous question, your compound it's CH3 and O. So this one has been confirmed. We said the fragment which its mass 31, actually has been confirmed that this bond here in the infrared. Let's go to the another technique, which is a proton NMR. Proton NMR, here we will see how many hydrogens we have. So the proton NMR spectrum of T, same compound, in CdCl3, this one deuterium chloroform. Deuterium chloroform, it's a solvent used in the NMR. Let's complete this table. 3.9, this is 3.9, we can see the peak, it's single. Okay, because it's single, that means here we have carbon bearing 3 hydrogens, and from the integration we have said it's 3 hydrogens. Now from the shape of the peak, it's a singlet. That means this carbon is bonded to, we cannot form 2 bonds, 1 bond. It's bonded to a carbon has 0 hydrogen or has oxygen. It's bonded to oxygen. Okay, so from the part per million, this range, which is 3.8 part per million, we can see from the data booklet this one for this group, when carbon holding 3 hydrogen, which is bonded directly to the directly to oxygen. So the compound has this group, which is this one, has been confirmed. So let's write it here. Type of proton, alkyl hydrogens bonded to oxygen. Now for this one, it's very clear the hydrogens of benzene. Okay, so this benzene. Now benzene, how many hydrogens? 6 hydrogens. But here how many hydrogens we have? We have 4. That means this benzene, it's di-substituted. Di-substituted, that means here we have something and another, that means could be this carbon or this one, this one, this one, this one. That means exactly, I don't know the second substituent, where is it, but we can say here. So here we have 2 substituents, so the number of hydrogens, it will be 4. Okay. Now in this question, the peak at 2.4 part per million is due to a proton attached to saturated carbon atom. Saturated, okay, that means it's here 2.4. That means these hydrogens, let's go to the mass spectra, NMR. Here we have 3 hydrogens. This is at 2.4. Okay, so this one 2.4 could be CH3, which is bonded here not to the oxygen, no, could be bonded to the carbonyl, or the CH3, which is bonded to the benzene ring. Okay, so these 2 possibles. Now then we have in the next question D2O, deuterium heavy water. This one, heavy water. Always heavy water is used in the NMR techniques to make sure we have this hydrogen which is bonded to the nitrogen, or the hydrogen which is bonded to the O. That means the hydroxyl group or amino group. But in the question, adding this heavy water to T doesn't change its proton NMR spectra. So that means T compound has no these groups. So now your compound could be benzene ring. We have two possibles. Benzene ring, okay, with, okay, now as we have here explained, so could be this CH3 bonded directly to the benzene ring, or like this one. Okay, and also we have this group which is CH3, this one, bonded directly to oxygen, single bond. So here we have how many carbons there right now? 1, 2, 3, 4, 6, 7. So as we have 7, that means this one here, okay, this one, okay, so here we have this one, okay, or now just 1 minute. Here for example we can say, okay, and here this one, let's do CH3, and here this one should be CH3. So now we have two possible structures. Now this one here we have single bond between this one and this one. Let's come back to the infrared spectroscopy. Infrared, this one, W. This W could be for this part. Here we have this one, W in the IR. Okay, this one, or this one here. This one. Okay, now V in the infrared spectroscopy, this one, or this one. Okay. Then in the NMR spectroscopy, sorry for that, in the NMR spectroscopy, the peak, which is CH3, which is bonded to the oxygen, this one, 3.8, this one, sorry for that, this one 3.8, or this one. And we have said we have 2.4 in the NMR, which is directly bonded to the carbon 0 or benzene ring. So this one in the proton NMR, or this one, which is 2.4. And in the benzene ring we have in the 7 to 8 with 4 hydrogen, these 4 hydrogen. Okay, so the compounds could be this one or this one. So the name of this first one, it's we can say para methoxy benzophenone. Benzophenone, yes, but here it's not included for your level, so I don't need to confuse you. And this one here also, it's methyl, here this one, it's methyl parabenzoate. Okay, but here we haven't asked about the names. And the next question, you have 4-nitro methylbenzene, which is this one, can be prepared by an electrophilic substitution reaction as shown. First of all, nitration by using concentrated nitric acid and sulfuric acid. We have this intermediate, and then we have formed 4-nitromethylbenzene. Okay, the reaction also form an isomer of 4-nitrobenzene. That means we will have another compound plus something. Okay, now at the end of the benzene chapter, okay, at the end of chapter of benzene compounds, we have the direction of this substitution if we are going to have a second substituent. So methyl group always is directing the second substituent to the position of 2, 4, and 6. Already what do we have? We have the substituent at position 4. So the second isomer should be this one. Again, this is benzene, and here this one methyl. So this compound. Okay, so we will form this another isomer, which is here. In this case, it will be 2-nitro methyl benzene. Write an equation for the reaction between HNO3 and H2SO4. So here forms electrophile. So here we are going to form the electrophile. So HNO3 plus 2 mole of H2SO4. Both of them should be concentrated. So here, and in the practical part, you need to drop the nitric acid over the sulfuric acid slowly, and the temperature should be very low. In this case here, you are going to form NO2 positive, okay, and plus H3O plus and 2 mole of HSO4 negative. Okay, so the nucleophile, the electrophile, which is used in the nitration, this one, has been formed by this reaction. In the next question, describe how the structure and bonding of 6-membered ring in the intermediate T differs from in methylbenzene. So here you need to compare this one with this one. Okay, so here in this case, just let me, in this compound we have comparison between this one and this one. Here the double bond is extended over how many carbons? Double bond extended over 6 carbons. But here the double bond is extended over only 5 carbons. So here pi bond only over 5 carbons. Okay. Then and about the hybridization. The hybridization here for this one, okay, so the 0.3 and 6 in the T you have carbon that is sp3 hybridization, this one, because here we don't have we don't have double bond, so this carbon here in this ring, it has sp3 hybridization. But all these carbons in the benzene ring, because here we have double bond, so the hybridization here it's sp2. Okay. As it's hybridization sp3, so the angle here it will be 109.5, but this one it will be 120. So 6 carbon has pi bond, and here 5 carbons have pi bonds. These carbons in the benzene ring, all of them, they have sp2 hybridization, but here only 5 carbons they have sp hybridization, but here only 1 carbon, this one, has sp3. So in this case the angle here it's 109.5 and here 120. Okay, so we can write here methyl benzene, and here intermediate T. Okay, here pi bond over 6 carbon, here pi bond over 5 carbons. 6 carbon has sp2, here 5 carbon has sp2, 1 carbon has sp3. I'm talking about in the benzene ring. Okay, angle here it's because double bond and sp2, so the angle here it's 120, but here for this carbon the sp3 the angle it's 100.5. so here we have 3 difference. Here in the next reaction or question, benzocaine is used as a local anesthetic. Okay, it can be synthesized from 4-nitrophenylbenzene. Okay, so nitro first of all is reduced into amino group, and this amino group is one of the it's substituted, that means one of the hydrogen is replaced with a acyl group, acylation, and then in the next reaction, step 3, this methyl group is converted into carboxylic acid. Okay, and then in the step 4 we have removed this acyl group and we have converted again into amino group with benzene, and then we have bonded to the carboxylic group ethyl group by reaction which is called esterification. Okay, so let's go to the questions. give the systematic name of W. Here is W. So this W, it's, what do we have? We have two substituents. So let's consider this substituent is carbon number 1, 2, 3, and this one 4. So 4, 4, amino benzoic acid. Okay, benzene and carboxylic acid. Here in the next question suggest the reagent and the condition for steps 1 to 5. In the step 1, when you have reduced the nitro group to the amino group, here we need to use this reducing agent, which is tin with HCl. Okay, tin with HCl. Both of them, we have to use them together, and you need to do reflux, or you can say heat, okay, to form the amino group. This one is reducing agent. Okay, in the step 2, you have removed one hydrogen from the amino group, and it's here, this reaction, it's acylation by using CH3 COCl, which is ethanoyl chloride. That means here you need to add CH3 COCl. Okay, and any alkyl group which is bonded to the benzene group, if you need to convert it into carboxylic acid, that means here your the reaction is oxidation reaction. So here you need to use KMnO4 in the acidic medium and reflux again. In the step 4, you have removed this acyl group. So removing the acyl group to the amino group, that means here you have used hydrolysis actually in the acidic medium. So that means HCl solution hydrolysis, okay, and you need to heat. And the last reaction, which is this one, carboxylic acid to ester. Which part, which it comes from the alcohol, 2 carbons you have added, that means you need ethanol. So here you need CH3 CH2OH, ethanol, in the acidic medium, which is some drops of H2SO4, and you need to heat or reflux. Okay, so this reaction is esterification, this reaction is hydrolysis, and this one oxidation, and this one acylation, and this one it's reduction reaction. This one is very nice question because has summarized all the reactions of benzene compounds. Now suggest how the basicity of benzocaine would compare to the ethylamine. So let's write the ethylamine, so CH3 CH2 NH2, okay, and benzocaine, this one, the last product, which is amine with benzene, and here you have CH2 CH3. The question about the basicity, actually this one more basic. Okay, why? Because here the basicity of amines it's depend on the density of these pair of electrons over the nitrogen. Here this alkyl group, alkyl is donating group of electron, while the benzene ring here is withdrawing a group. That means the density of this electron, it will be decreased because the benzene ring will take or decrease the density of this electron. So the presence of this pair of electrons on the nitrogen, it will be less than the presence of these pair of electrons in the ethylamine. So this one, it will be less basicity or than the ethylamine. That means the pH of this one is higher than this one. Here a sample of benzocaine shown below was analyzed by proton NMR and carbon-13 NMR spectroscopy. Predict the number of peaks that would be seen in the carbon-13 NMR. Here, let's count how many different carbons, okay, how many different carbons in this compound. Here we have 1, 2, 3, and this one 4. These two carbons, okay, are similar, so we will count them as a 1 carbon. So here 1, and same thing for these two carbons. They are similar because this part is similar to, that means this part with this part is similar, okay, symmetric compound, okay, or this, I mean this part, not all of the compound. So we will count only this carbon, and here this carbon, it's 1. So 1, 2, 3, 4, 5, 6, 7 carbons. So in the carbon-13 NMR spectrum, you would be seeing 7 peaks. Okay. In the next question, benzocaine was dissolved in deuterium chloroform, and the proton NMR, here it's a proton, the another technique, spectrum of this solution was recorded. Here suggest why CdCl3 and not CHCl3 in the proton NMR. Okay, why? Because hydrogen of CHCl3 would be seen in HNMR. Okay, proton NMR. So, but by using this solvent here, we have 0 proton. So 0 proton, that means we don't have any proton comes from another source. But if you will use the CHCl3, already your compound has a proton, and this solvent has a proton, so you'll have always extra protons, so it's not easy to analyze your compound. So here, use the data booklet and the spectrum in the previous question to complete the table for the proton NMR spectrum of benzocaine, the actual chemical shifts, or sometimes we are using part per million for the 4 absorptions have been added. So group responsible for the peak, which is from 7.1 to 7.4, this one for hydrogen of benzene. Number of hydrogen atoms responsible for the peak, let's check it. So actually it's only 4. 1, 2, 3, 4. And the shape of this peak, it's multiplet. For 5.5, 5.5, this one, 5.5. This one, it's very clear for nitrogen, which is this one, hydrogen of amino groups. Okay, so we have 2 hydrogens, and the shape, how is it in the, it's singlet. Okay, always is formed as a singlet. NH2 or OH, always they are singlet, but OH, it will be 1 hydrogen is responsible for the NH. This one, it's a 2. That means here the integration for this one is 2H. And for this, now we have solved this one, 3.5. It's 3.5. This one, 3.5. It's very clear. That means this one, it's a carbon which is holding the hydrogen, which is bonded directly to the oxygen. So the carbon which is holding hydrogen and directly to the oxygen, this one. So this one is for CH2. This one. So here we have 2 hydrogen, and the splitting pattern, how is it, is a quartet. It's quartet. Okay, and the last one, which is this one, which is very far from any electronegative atom, which is this CH3, this CH3. So here we can see this CH3. Okay, 3 hydrogen alkyl group. That means hydrogen of CH3 is bonded to the carbon, and 3 hydrogens, and the shape is it's doublet. Sorry, it's let's check it. It's a triplet. Now let me explain why it's triplet or why it's a quartet. According to this rule, n plus 1. Now I'm talking about CH3. The integration, it's 3H. Here, from the integration, the length of this peak, it's 3 hydrogen. Okay, but I'm talking now about the shape of this peak, why it's triplet. Now, what's the neighbor of this group? The neighbor, this one, CH2. So CH2, how many hydrogen has? Has 2 hydrogen. So N, it's 2 plus 1 equal what? 3. So the shape of this peak, it will be triplet. Now let's apply the same rule for CH2. CH2, what's the shape of CH2? Now CH2, the neighbors, this. So this one has 0 hydrogen and this one has 3 hydrogen. So N it's 3 now. Plus 1, it will give us 4. So the shape it will be quartet. So always the splitting pattern, it's depend on the rule, which is N plus 1. N, the neighbor carbons, the number of hydrogens of neighbor carbons. Okay. So I think we have a question about this one. So here, look to this question. Explain the splitting pattern of 1.2. That means this one. The rule, it's N plus 1. The neighbors of this one, now CH3, the neighbor, it's CH2. So the neighbor has 2 hydrogen, plus 1, so this one it will give us 3, and the shape is triplet. Okay. The proton NMR spectrum of benzocaine dissolved in heavy water, deuterium water, okay, was recorded. Now ask yourself, in your compound, do we have or NH or OH? Yes, we have NH2. So this compound, if you will dissolve it in D2O, at once the peak which is responsible for NH2, it will be disappeared. That means this one, this peak, exactly this one, it will be disappeared. Okay, so let's come back to the question. Suggest how this spectrum would differ. That means the peak of NH2 will disappear. Okay, why? Because we will have exchange. That means your compound, this one it was, you will have here the CO and CH2, CH3. Here it's not important, I'm focusing on NH2. So this one, when it will be reacted with DTO, at once you will have exchange this hydrogen with D. So your compound, it will be here, this one, it will be N DT. So your compound has lost these 2 hydrogens, and deuterium, because it has even number of, that means even nucleon number, and the NMR spectroscopy always detect the nucleus with odd number. So deuterium has even number, because deuterium, it's 1 proton, yes, but the nucleon, it's 2. So this one, it will not be detected in the NMR. Okay, so we have lost this peak, which is responsible for NH. Okay, benzocaine can also be used to synthesize the distuff S by the following route, R and S. So distuff, that means and from amine compounds, at once you need to think about diazonium salt. Okay, so now the question suggest the reagent used for step 1. So to form the diazonium salt, you need to use this mixture of Na, so just let me change the color, Na, NO2 with HCl, and temperature should be less than 5 Celsius. Sometimes 10 Celsius, it's okay. Or you can use, you can say this one, another one, NaNO2. Okay, with this temperature, at once you will form this compound. CO2, CH2, CH3. Here the NH2, it will be converted into diazo. Okay, so this one, diazo salt, diazonium salt. Let's write it, diazonium salt. Why it's salt? Because this is positive here, okay, and it will be bonded with the chloride. Then when you will react it with the phenol in the presence of alkali, you will form this distuff. The distuff, you will bond your compound. This is your compound. This one I'm talking about it. CO2, CH2, CH3, and then this nitrogen, it will be, just let me clear it. And this compound, it will be bonded from position number 4, so then your phenol. This one, the distuff. Okay, so we have suggested the reagent, we call it, it's NaNO2, or you can say Na. Sorry for that. You can say NaNO2 in the presence of HCl, or just you can say HNO2. So just let me correct this one in the box. This one HNO2, nitrous acid. Okay, nitrous acid. And the suggested structure are S and S, we have completed in the boxes. In the question 8, compound A can be produced from a plant hormone. Okay, we have this one. Compound A shows optical and geometrical isomerism. Geometric, that means cis-trans. Optical, you need to find the chiral center. Now, on the structure of A above, draw a line through the bonds that give rise to geometrical isomerism. So here you need to geometrical isomerism. So where is the geometrical isomerism? Could be this one and this one. Okay. So we have, then circle all chiral carbon atoms. Here you need to find the carbon which is bonded to the 4 different groups. So this carbon. So here, circle, we have circled this carbon. Give the name of 4 functional groups present in A. So let's start with this one. This one is ketone. carbonyl, and this one alkene, you can say, double bond. You have this one carboxylic acid, and you have OH, which is alcohol, this one. We have named these four different groups, functional group. A molecule of A has 17 carbon atoms. State the number of carbon atoms that are sp, sp2, sp3. Always sp, that means you have triple bond. sp2, double bond. sp3, it's all of them are single bond, all the bonds. So let's go to the structure and we will see. Let's clean this structure. Okay. Do we have triple bond? No. So sp0, sp2, 1, 2, 3, 4, 5, 6, 7, 8. 8. So sp3, 1, 2, 3, 4, 5, 6, 7. Have we missed any carbon? So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Here 1, 2, 3, 4, 5, 6, 7, 8. So sp3. So this one's 16, but here 17. Wait, this one and this one. Okay, this one. So sp3, it's 9. Okay. So sp0, sp2, 8, and this one 9. When A is reacted with an excess of hot concentrated manganate ion, a mixture of 3 organic compound is formed. Okay. So he's asking about the one with the 3 carbons and the one with 4 carbons. So let's go to the compound. Again, let's hot manganate. That means you need to break down the compound. Your compound, it will be broken from this part. So this carbon, this part between these two lines, 1, 2, 3. So here, the first one, it will be this one. Here, and OH, and this one O. So this one is C3, 1, 2, 3. How many hydrogen here? 3, 4, and 3 oxygen. The other part, already here we have carboxylic acid, H, O, carbonyl. Then this one, it will be ketone and CH3. So this one, how many carbons? 1, 2, 3, 4.
C4, hydrogen 3, 5, 6, H6 and O3 again. So the first one, C3H4O3, C3H4O3, this one, it's already drawn above, and C4H6O3 also we have drawn. And this about chromatography, TLC, thin layer chromatography. So a mixture of 3 different compounds, J, K, and L, was analyzed by thin layer chromatography, TLC, using a polar stationary phase. That means the polar stationary phase, it's aluminum oxide or sometimes silica, and non-polar mobile phase. The non-polar mobile phase, that means non-polar organic solvent. The 3 compounds all have similar molecular masses. The resulting chromatogram is shown here. Your solvent, it's non-polar.